So we've talked about the first derivative test, and now that was using the mean value theorem to determine over an interval when a function is increasing or decreasing. And we used that to determine whether a critical point was a local maxima or a local minima. What we want to get into now is actually being able to start sketching curves with more detail. Now, not a whole lot of detail, but at least enough detail to get a real sense of how the function is changing. And in order to do that, it's not enough to just use information about the first derivative. So in some sense, when you see first derivative, you should think increasing, decreasing. But what about the actual slope of the function? So the first derivative essentially says that the slope is positive or the slope is negative. But the derivative itself is a function. So you can actually ask the question, is the derivative increasing or decreasing? This is information about the second derivative. So the second derivative is going to tell us the following. Our function has an increasing rate or a decreasing rate. And when I say rate, I mean rate of change. Decreasing rate of change. And this can be a little bit confusing if you just kind of accept this abstract way of thinking. Okay, so the first derivative says the function is increasing or it's decreasing. Now, regardless of whether the function is increasing or decreasing, the function can have an increasing rate of change or a decreasing rate of change. And what I like to do here is really hold on to a concrete physical application. And the example I like to use is driving in a car. Because really everything you can do in a car can illustrate everything we need to know about how the first derivative and the second derivative describe how a function is changing. So think about your car. Now, first of all, you can go forward in your car. So this is increasing my position. If I'm moving forward, my position is increasing. So the fact that it's increasing is more or less just an orientation. I'm going forward, so my position is increasing. My position can also decrease. So I could have a decreasing position. Okay, this is all information about the first derivative. I'm just describing the velocity of the car. Is the velocity positive or negative? If my velocity is positive, my position is increasing. If my velocity is negative, my position is decreasing. I'm going backwards. Okay, but whether or not I'm going backwards or forwards, I can make a choice. I can either be pressing on the accelerator or pressing on the brake. Okay, so that's going to describe whether or not my rate of change is increasing or decreasing. So if I'm moving forward, I can be accelerating. So accelerating means increasing rate of change. So I'll put ROC for rate of change. So I can be moving forward and I can be accelerating, increasing my rate of change. But I can also be moving forward and decelerating, or braking, as we like to call it. So decelerating or braking. But the point is, if I'm braking and moving forward, I'm decreasing my rate of change. Okay, so I can be moving forward, and then I can be accelerating or braking. That's changing my rate of change. It's kind of strange. You're changing your rate of change. But I can also be moving backwards. And the interesting thing about moving backwards is that if I'm moving backwards, I'm decreasing my position. How do I increase my rate of change? Well, I actually increase my rate of change by braking. So if I'm moving backwards and I'm braking, I am increasing my rate of change. But if I'm moving backwards, if I'm in reverse, and I guess I have to put the car in drive, and I accelerate forward, so I have the car not in reverse, but actually in first gear or whatever, and I press on the accelerator to move the car forward, let's see. No, okay, so if I'm getting confused. Let's see. So it's a very subtle thing. So let's stop and think about it. So if I'm going backwards and I'm braking, I'm increasing my rate of change. Even though I'm slowing down, my acceleration is actually moving me in the forward direction. That's what's actually slowing me down. But if I'm in reverse and I accelerate, so I accelerate backwards, I'm decreasing my rate of change. Okay, so depending on whether I'm moving forward or backward, braking or accelerating will either increase or decrease my rate of change. So increasing rate of change is always acceleration in the forward direction. So even though if I have the car in reverse, I'm technically accelerating, but I'm accelerating myself in a negative direction. So I actually consider that as a decreasing rate of change. So that, I think that's the most confusing thing, is when I'm actually moving backwards, it's a little bit switched from the way you might think about it. Okay, but try to really understand this example, because if you can just sort of digest what I sort of spit out right there at you, then you're going to go a long way to understanding basically the four cases that can come up with the interaction between the first and, of course, the second derivative. So all of this was about the second derivative. So let's look at actually what all of these four cases look like as graphs. Okay, so the first thing we want to make note of is actually how we describe when the second derivative is positive and negative and what that means about the function itself. So if the second derivative of a function is greater than 0, well, what that means kind of in our previous discussion is that we have an increasing rate of change. So another way to say that is f is concave up on this interval. Now, you can also tell that a function is concave up by looking at its graph. So a function that's concave up is going to have a right side up bowl shape, like we have here in blue. So this is a concave up graph. Now, if the second derivative is negative on an open interval, then what that means is that the function, so the derivative is negative, so we have a decreasing rate of change on that interval. and we say that the function is concave down. So it's pretty easy. Up, second derivative positive, down, second derivative negative, decreasing rate of change, increasing rate of change. And so concave down looks kind of like a bowl that's been turned upside down, like that. Or you can think happy face, sad face, positive, negative, up, down. Okay, so there's a lot of connections between all the words that help you remember what concave up means, what concave down means. Concave up, positive second derivative, derivative is increasing, looks like right side up bowl. Concave down, second derivative negative, derivative decreasing, upside down bowl. Okay, so it's important to make all of those connections. So I encourage you to kind of just really write it out yourself and just, think about it. Again, all of these things are more or less saying the same thing. And this is important because of this table here. And this is really the key table for curve sketching right here, because there are 4 cases that we could have for the graph of a function. And they actually correspond to the 4 cases we talked about with the car. Moving forward, accelerating, moving forward, braking, moving backward, accelerating forward or braking, and then moving backward and decelerating, so actually accelerating in reverse. So we see that whether the function is increasing or decreasing just depends on the sign of the first derivative, and then whether or not the function is concave up or concave down, or in other words has an increasing or decreasing rate of change, only depends on the second derivative. So the first case, the description is that f of x is increasing at an increasing rate. So both the first and second derivatives are positive. We're just considering a small little piece, a small open interval. Then the graph, so the function is going to be increasing, but notice that there are different ways a function can increase. So if I say the function is increasing, it could look like that, it could be concave up, or it could be concave down. So those are sort of the examples of how a function can increase. It can sort of have no concavity, it can be flat, it can be kind of bowed down or bowed up. Okay, and then the same thing, if a function's decreasing, it can be bowed up and decreasing, or it can be bowed down and decreasing. And whether or not it's bowed up or bowed down is whether it's concave up or concave down. So next, if f is increasing at a decreasing rate, then it's bowed up like this. So you can see that it's actually concave down. It's like a piece of a bowl that's turned upside down. But it is actually increasing. Then next, of course, the function can be decreasing at an increasing rate, so it can be concave up. And then the function can be decreasing at a decreasing rate, so it can be decreasing and concave down. So there are 4 cases to get straight. Increasing at an increasing rate, increasing at a decreasing rate, decreasing at an increasing rate, decreasing at a decreasing rate, derivative positive, second derivative positive, second derivative negative, second derivative positive, derivative negative, second derivative negative. This is sort of like what the pieces of the graph look like. So when we actually get into curve sketching, you're going to break up the domain of the function into pieces that fall into these 4 cases. So on each one of those intervals that you determine, okay, on this interval, the first derivative is positive and the second derivative is positive, the graph needs to look like this, and then so on. Okay, so hopefully, I'm intentionally saying it a lot of different ways multiple times, just to kind of get you to get a sense of how it can be said. But if you're getting overwhelmed, just take a deep breath, because all of this really means the same thing. There's just 4 things to remember, and there's a bunch of different ways to say those 4 things, but you just need to be familiar with these 4 cases so that when you identify them out of a function, you can accurately sketch whether the function is increasing or decreasing, and then whether or not the function is concave up or concave down. All right, so before we practice curve sketching, let's actually nail down a little bit more about the second derivative and just a little bit more terminology, of course. There's always more terminology to learn. So the basic idea is that the second derivative of course, we're assuming that a function is what's called twice differentiable, which basically just means that it's differentiable and then the derivative function is also differentiable. So the second derivative, f double prime of x, gives the concavity. That's what we were just talking about. If the second derivative is positive, it's concave up. If the second derivative is negative, f of x is concave down. Okay, so a point x equals a, where f of x changes concavity, is called an inflection point. So this is similar to the idea of a local max or a local min. And in fact, if you're assuming that the function is twice differentiable, an inflection point of the function will either be a local max or a local min of the derivative function. So you sort of get this chain of functions. You have the function, the derivative, and the second derivative, and all of them are saying different information about each other. Okay. So if the second derivative changes from being positive to negative, since the second derivative is the derivative of the function, that means that the derivative has either a local max or a local min. So with that being said, candidates for inflection points are x values for which f double prime of x is 0. And this is exactly what I just said. Okay, so if we are looking for inflection points, we're looking for local extrema of the derivative function. So in other words, we're looking for critical points of the derivative. Okay? Because again, assuming the function is twice differentiable, an inflection point is nothing more than a point where the second derivative changes signs, because the second derivative gives the concavity. Okay, so just to kind of illustrate what an inflection point is via a graph, let's just look at kind of what a typical inflection point will look like. Now again, because we're only thinking about inflection points, the function could be increasing or decreasing or whatever. That doesn't really matter. But an inflection point goes something like this. It's going to be, say, concave down and then concave up, like this. So here we have our inflection point. And so this is sort of what we call a saddle point, but I mean, don't get too caught up in just language. Precisely what I mean by inflection point here is a point where to the left of that point, the function is concave down, or vice versa, of course. And then to the right, it's concave up, or vice versa. So it's just changing concavity, or the second derivative is changing sign. Okay, so that's the idea behind inflection points. They're just like local extrema, but they're going to be important to identify when we're curve sketching because, again, we want to break up the graph of the function into regions that fall into one of those four cases that we described previously. Okay, one more thing that's not 100% necessary, but it does come in handy if you can remember it. So recall that with the first derivative test, if we had a critical point of the function, and the derivative changed from being positive to negative or negative to positive, we can conclude based on those two cases whether or not that critical point was where a local maximum or a local minimum occurred. So the second derivative test works very similarly, but you don't actually have to choose points on either side of the critical point like we did for the first derivative test. But the payback is it doesn't always work. Okay, so if we have a critical point of the function and we take the second derivative and evaluate the critical point at the second derivative and it's positive, so in other words, if a function is concave up at a critical point, then it's a local maximum. And the graph is really all you need to see. If you're concave up and you have a vertical tangent, then you have to be a maximum. And if you're concave down and you have a vertical tangent, then you have to be a minimum. So it's really cool to remember. It's a little bit easier to apply than the first derivative test. But of course there's a catch, like I said. What if f prime of c is 0 and f double prime of c is 0? Or f prime of c is undefined? Well, in these two cases, unfortunately, the second derivative test is inconclusive. And so what do? You use the first derivative test. So it's great, it's really nice. Like I said, I think it's easier to use than sort of testing points to the left and the right, but it has the caveat that it does not always work. In the case that the second derivative is 0, where you actually don't know the concavity, of course you can't conclude anything. And then if the critical point is coming from the fact that the derivative is undefined, unfortunately you also typically cannot use the second derivative test. Okay, so curve sketching is one of the trickiest parts of this class. Now, maybe some people would disagree with me, but I agree with me, so that's all that really matters, and I'm talking right now. So the reason I think that curve sketching is so tricky, so what I mean by curve sketching is just I give you f of x equals blah blah blah, and then I tell you sketch the curve relatively accurately. The first challenge is, there are different levels of accuracy. Now, the level of accuracy we're going to focus on is the first derivative and the second derivative. So accurately portraying where the function is increasing or decreasing and where it's concave up and down. And you'll see that I have that in the final step, that should be accurately portrayed. And now you may ask, well, why don't we use the third derivative or the fourth derivative? And that's a really good question. Now, certainly we could determine information about the function from the third and fourth derivative. But this actually is not so important because our I really only has the ability to differentiate between increasing, decreasing, concave up, and concave down. Now, if I lined up a bunch of graphs, you could probably say which one is more concave up or concave down, but just looking at the graph of the function, you don't really get any more feel for what the function is doing by looking at higher derivatives. So it really is, from a visual standpoint, as accurate as you need to be, whether or not the function is concave up or concave down. Okay, so that's all I want to say about that. So that's what I mean by curve sketching. Accurately, and pretty accurately, pretty visually accurately sketching the curve. And the other reason I think curve sketching is difficult, other than just, it just is, believe me, is because there are so many things to do. So you have to figure out information about the first derivative, figure out information about the second derivative, be very organized in either making a table or some number lines to sort of really see when is the function concave up and increasing, when is it concave down and decreasing, etc. So I say all this to say that here's my general guidelines. This is more or less what I do. So notice the first one is really nice. You know you need information about the first and second derivative. So if you're trying to sketch the graph of a function, then just take the derivatives. You know you're going to need the first derivative and the second derivative. And then also, an important part of the graph of the function are local extrema and inflection points. Okay, those are going to kind of break up your increasing, decreasing, concave up, concave down. So to find those potential extrema and potential inflection points, you want to set the derivative you want to set the first derivative and the second derivative equal to 0, and also see where they're undefined. Next, you want to determine the critical points, like I said, by setting those equal to 0, and then using the first or second derivative test, really determine which ones of those critical points are local extrema, and then which one of the critical points of the derivative are inflection points. So actually nail down the extrema and the inflection points. Then that should give you the intervals for which f is increasing, decreasing, concave up, concave down. The only other thing is number 4. Now, we really haven't talked about this in the last couple of lectures, but it's something to keep in mind, because as you're sketching the graph of the function, at some point you just sort of need to let the function go, right? Let it do whatever it's going to do. But then it's really important to know the end behavior. Is the function leveling off to a horizontal asymptote? Is it going to infinity? Is it going to positive infinity? Things like, what is the domain of the function? Are you making sure that you're only plotting in regions where the function is defined? So 4 is kind of a catch-all for just, things that are kind of outside of just what's going on in this little interval here. Is it concave up, concave down, increasing, decreasing? And then finally, 5 is just do it. Okay, so I like to plot the critical points, the inflection points, and the intercepts. Okay, where does it cross the x-axis? Where does it cross the y-axis? Again, not all of this is necessary. I don't think you need to plot 100 points and then connect the dot. I really just think you need to plot the extrema, the critical points, the inflection points, and like I said, I like to do the intercepts because that's just another degree of accuracy that's not too hard to do. It's easy to find the y-intercept, and typically not too hard to find the x-intercepts. And then the last part is the most important. You play connect the dots, but you connect the dots in a way so that if the function is increasing and concave down between those two dots, you make sure to draw the function increasing and concave down. And then you do your best to kind of connect the dots in a way so that the function looks somewhat like a function. Okay, and I am not a very good artist, and in the examples I have actually used a computer to graph the function for us, so I'm sort of cheating, but I don't think you need to be a great artist to sketch the graph of functions. I think you need to be technically accurate, and that's where it comes back down to, are you making sure to portray increasing, decreasing, concave up, concave down, and then connecting the dots. And if you do that, then you'll be on your way to really being able to understand what functions look like without using, say, a graphing calculator. Alrighty, so here's our first example, and we're going to have some functions, and we want to find the intervals for which they're increasing or decreasing, the local extrema, that sounds familiar, but then we also want to do a little bit of practice finding the intervals of concavity and the inflection points. Okay, so this is going to kind of be a primer for doing a couple of just all-in curve sketching problems. Okay, so specifically, we've done this and this before. Maybe to find the local extrema, maybe we can practice using the second derivative test and seeing how that works. And then finally, looking at the concavity, okay, and the inflection points. So like I said before, you should not even think. Your first step should just be to take derivatives, okay? And we know we're going to need up to the second derivative. So f prime of x is 6x squared minus 6x minus 12. And then the second derivative is 12x minus 6. Okay, so let's start with the first derivative. So in other words, let's talk just for now about where the function is increasing or decreasing in the local extrema. So to do that, we need to find the critical points of f prime. So if we set f prime equal to 0, notice that, okay, I'm setting 6x squared minus 6x minus 12 equal to 0. I can certainly cancel a factor of 6. So all the coefficients have a factor of 6. So f prime being 0 is really the same thing as asking, when is x squared minus x minus 2 equal to 0? And as we hoped, this factors is x minus 2 times x plus 1. Okay? And let's see what else. So we get two critical points, x equals 2 and x equals negative 1. So before we find the intervals of increase or decrease, let's actually try to use the second derivative test to see whether or not x equals 2 or x equals negative 1 are where local extrema occur. Okay, so f double prime of 2 is what? Well, remember, we don't even care what the actual value is. I just want to know whether it's positive or negative. Well, it's going to be positive, right? Because 12 times 2 is a lot bigger than 6. So it's positive. But what that means is that f of 2, okay, and what is f of 2? F of 2 is negative 20. So you have a critical point. Specifically, you have a horizontal tangent. where a function is concave up. Remember what concave up looks like. It looks like this. So we can conclude right away that f of 2, which is negative 20, is a local max. Sorry, is a local min. Local min. And this is again by the second derivative test. Okay, second derivative test, because it's concave up, the critical point is where a local min will occur. Very good. So now let's use the second derivative test to test x equals negative 1. So what is f double prime of negative 1? Well, we don't need to do a lot of work. It's negative, right? Because it's going to be a negative minus 6, so that's going to still be negative. So it's negative. But that tells us, recall, that the function has a horizontal tangent and is concave down. So that means we have a local max. So f of negative 1, and what is f of negative 1? Looks like it is negative, let's see, no, it's 7. F of negative 1 is 7, should be. Double check that. Is a local max. Alrighty, very good. So notice I'm doing this a little bit out of order here, but that's okay. You know, I just need to find all of this. So, you know, you just need to start. And maybe you find your own way that makes more sense to you, and that's fine too. But actually, to list the intervals where the function is increasing or decreasing is relatively easy now. So notice that because we have a min at 2 and a max at 1, that means I should be increasing before negative 1. Because I know that the function changes from being increasing to decreasing in negative 1 because it's a local max. And then between negative 1 and 2, it should be decreasing. And then after 2, it should also be increasing because 2 is a local min. So it changes from being decreasing to increasing. So it's also increasing from 2 to infinity. And then f is decreasing like we said, between negative 1 and 2. And remember, I know this, I'm just using the fact that negative 1 is a max, is where a max occurs, and x equals 2 is where a min occurs. And that's it. Okay, so I know the general shape. I know it dips down and then dips up and then goes back down. Okay, so now all that we have left is to talk about the second derivative. So notice, when does the second derivative equal to 0? So we're looking for the critical point of the first derivative. And this happens, okay, so we set 12x equal to 6 because, right, we want this to be 0. So it looks like x equals 1/2 is a critical point of the first derivative. So it's a potential inflection point. And also, it's really easy to see, if I take a number less than 1/2, then the derivative will be negative. And if I take a number bigger than 1/2, the second derivative will be positive. So at x equals 1/2, f double prime changes from negative to positive. But what does that mean about the concavity of f? It means that f changes from being concave down to concave up. So x equals 1/2 is an inflection point. Okay, looking good. And then the last thing to say is just the intervals of concavity. So in other words, the intervals where the function is concave up versus concave down, well, we already see what that is. So f is concave down where, well, from negative infinity to 1/2, and then f is concave up from 1/2 to infinity. And that's just using the sign of the second derivative. So one other thing I'll mention, when we say that x equals 1/2 is an inflection point, there's some kind of difference in opinion that I've seen about what you call an inflection point. Now you might say that like the actual point 1/2 comma f of 1/2 is the inflection point. I'm sort of lazy about it. I just say, okay, there's an inflection point at x equals 1/2. X equals 1/2 is the inflection point. Doesn't really matter. When we curve sketch, we'll actually find the function value for the inflection point too, so we can plot it. But for now, I mean, this is enough to identify where an inflection point occurs. Okay, so as you can see, there's a lot going on here. But this is really enough information for us to sketch the graph of this function. All right, so let's do the same thing with this function g of x times square root of x plus 1. So again, these problems are a little daunting because there's a lot to do, so just take a deep breath and do the easy thing first. Take the derivative, okay, and the second derivative. So what is the first derivative? Well, we have a little bit of product rule to do. So this should be square root of x plus 1. So derivative of x is 1 plus x over 2 square root of x plus 1. And now, I don't really like the form that this is in, so I'm actually going to get a common denominator. So I'm going to put this over 1, and I'm going to multiply this first term by 2 times square root of x plus 1 on top and bottom. And so what I get, okay, so that'll just become x plus 1 times 2, so 2x plus 2 plus x, so it looks like 3x plus 2 all over 2 square root of x plus 1. Okay, so easy enough. Now, we need to take the second derivative. So this is g prime. We need to take the second derivative, which involves doing the quotient rule. So so kind of just to save space, I'm just going to do some scratch work over here and then I'll erase it and just put the answer. So we need to do low d high minus high d low over low squared. So let's see. This will be 2 square root of x plus 1 times 3 minus 3x plus 2, and then times 1 over square root of x plus 1. So that's the derivative of this, all over 4 times x plus 1, square root of x plus 1 squared, which is x plus 1. Okay, and so what I'm going to do is I'm going to get a common denominator again. So this is like over 1, so I'll multiply by square root of x plus 1. So it looks like we have 2, so this is 6 times x plus 1, so 6x plus 6 minus 3x plus 2 all over 4, and then the square root of x plus 1 can combine and give us x plus 1 to the 3 halves. I really only am interested in the numerator, so this is going to be 3x plus 4 over 4 times x plus 1 to the 3 halves. Okay, that looks good. So the second derivative, simplified, and again, the simplification process here is really crucial for finding things like where these derivatives are 0, times 4, let's see, over 4 times x plus 1 to the 3 halves. Okay, and we'll just erase all that. And here we go. So we have the first and second derivative. Wonderful. Make sure that you double check and you believe me that you can simplify the derivatives. So that's some algebra. Hardest part here is going to be algebra, but it's not the part I want to dwell on. So let's start with information about the first derivative. So for the first derivative, we have what? When does g prime equal 0? Well, that's when x is equal to what? Negative 2/3. Okay, that's pretty easy to see. And so what about when g prime is undefined? Well, that's going to be when x is negative 1. Okay, so we can use the second derivative test for x equals negative 2/3. So we have g double prime of negative 2/3. That's going to be what? Negative 2 plus 4, so that's going to be positive. And the denominator is also going to be positive, so this is greater than 0. So what does that tell us? Well, that tells us that g of negative 2/3 is a local minimum because the function is concave up. So g of negative 2/3 by the second derivative test, which is, we can evaluate that, 2 over 3 root 3 is a local min. Okay, so that's good. And now because g prime is undefined, unfortunately we can't use the second derivative test for x equals negative 1. But let's just think about what's happening here. Notice, what is the domain of g? So this is a very important question to consider, at least at some point. What is the domain of g? Well, it's not going to actually make sense to plug in anything less than negative 1. So the domain is negative 1 to infinity. So I can't use the first derivative test and say, okay, to the left of negative 1, this is happening, to the right, this is happening. X equals negative 1 is actually just the endpoint of the domain. So I just need to look immediately to the right. But let's just plug in, say, x equals 0. If I plug in x equals 0, the first derivative is positive. That means the function is increasing as we move away from -1. But that means that x equals -1 is where a local min occurs. Okay? Good, good, good. So because g prime, let's see, so is that right? -2/3. Well, okay, so we need to be a little bit careful because we need to test in between these two critical points. So it actually seems like, let's say we plug in something like a -0.9. Okay, so that'll be -2.7 plus 2, so that'll actually be negative. So actually immediately to the right of x equals -1, g prime is less than 0, just to the right. Of x equals -1. So it's actually decreasing, so that's interesting. So it's decreasing. So that actually means that we have a maximum, a local maximum at x equals -1. So g of -1, which is 0, is a local max. And again, that's because, now I can't plug in 0. I know I plugged in 0 first, but I have to look in between these two critical points, -1 and -2/3. So I just take a number really close to -1, so just to the right of -1, like -0.9, and I evaluate the derivative and find that it's negative, just to the right of x equals -1. So it's going to be decreasing, and then at -2/3 it'll start increasing. So that actually tells us our intervals of increase and decrease too. So g is decreasing from -1 to -2/3, and then g is increasing from -2/3 to infinity for the rest of the domain. Okay, cool. So hopefully that makes sense. It can be a little tricky to kind of reason through all of this, but that's what we have. Now let's move on to the second derivative. When does g double prime equal 0? Well, again, it's not too hard to see. It's when x is equal to -4/3. And notice that g double prime is undefined at x equals -1, but that's not a critical point of g prime because g prime is also undefined at -1. So we really only have one critical point of our first derivative. So one potential inflection point. And so we notice again that g double prime, so if we look down here, so if we plug in, let's see, so -4/3. Well, actually, okay, so this is interesting. So x equals -4/3 is actually not in the domain of the function, right? So even though this is a critical point, right, it's actually not in the domain. So not in domain. Thus not a critical point. So what does that mean? That means there are no inflection points. There are no potential inflection points, therefore there are no inflection points. Okay, so even though we set the numerator equal to 0 and x equals -4/3 made the numerator 0, it's not defined in the function itself. Okay, it's in the part of the function that doesn't exist. So that's really nice. So we just have to test one point in the domain of the function to see whether or not this function is concave up or concave down over its entire domain. Let's just plug in 0. So if we plug in 0, g double prime of 0 is positive. So what does that mean? Well, that means g of x is always concave up. Or it's concave up over its whole domain. Now, sort of conventionally, we just kind of include open intervals for concavity and increasing and decreasing, because it's a little ambiguous what we mean by the concavity at an endpoint of an interval. Okay, so g is concave up over its entire domain. Okay, so last problem in this example. We have the function h of t equals sine squared t. So let's take some derivatives. What's the first derivative? Looks like we need to do a little bit of chain rule. So 2 sine t to the first, and then times the derivative of sine, which is cosine t. And then the second derivative, well, we have this constant multiple 2, which isn't going to affect too much. And then we need to do a product rule. So if I take the derivative of sine first, I'll get cosine times cosine, so cosine squared. And then if I take the derivative of cosine, I get negative sine, so that should be negative sine squared t. Very good. So let's think about when h prime equals 0. Well, for h prime to be 0, I either need sine to be 0 or cosine to be 0. So here are the values that will make sine or cosine 0. So 0 will make sine 0. Pi over 2 will make cosine 0. Pi will make sine 0. 3 pi over 2 will make cosine 0. And then finally, 2 pi will make sine 0. So there are our critical points. And the nice thing is we can very quickly just apply the second derivative test. So what is h double prime of 0? Well, there's this factor of 2 that's not going to change the sign, but it's just 1 minus 0, so it's positive. Then h double prime of pi over 2 is going to be 0 minus 1, so that's negative. And then for pi, it's going to be positive again. 1 minus 0. Really it's negative 1 squared minus 0, but 1 minus 0. H double prime of 3 pi over 2. That's going to be negative, because 0 minus negative 1 squared. And then finally, h double prime of 2 pi will be positive again. So our values here are going to be h of 0, which is 0. H of pi over 2 is 1. H of pi is 0. H of 3 pi over 2 is negative 1 squared, which is still 1. And then h of 2 pi is 0. And just by the concavity, I can see which are local max and local min. This will be a local min. This will be a local max because it's concave down. This will be a local min. This will be a local max. And this will be a local min. Okay, and then we also see immediately from this the intervals where h is increasing or decreasing. So h is going to be increasing. So this is a min, so it's going to be increasing after, so between 0 and pi over 2. It's going to be decreasing after pi over 2 to 0, because this is a max. And then basically between a min and a max, it'll be increasing. So between pi and 3 pi over 2, and then h will be decreasing on the other gaps, so between pi over 2 and pi. And then 3 pi over 2 and 2 pi. Alrighty. So that was pretty straightforward. So you see the value in the second derivative test, that we didn't actually have to line up all 4 of these critical points, or I guess actually 5 of these critical points, and test values in between all of them. We could just use the second derivative, and that actually tells us about the increasing and decreasing around those critical points as well. So now let's shift our attention to the second derivative. Here we go. So when is h double prime equal to 0? So now that's going to be basically when sine equals cosine up to a sine. So it could be, plus minus or whatever. So we want cosine squared t to equal sine squared t. So in other words, absolute value of cosine t to equal absolute value of sine t. So remember, when we take the square root, we have absolute values. And so when does this happen? Well, t equals, okay, when is sine and cosine equal? Just go look at the unit circle. Well, that's like pi over 4, 3 pi over 4. Now at 3 pi over 4, cosine is negative and sine is positive, but that's okay because I'm squaring both of them. And then 5 pi over 4 and 7 pi over 4. So 3 pi over 4. Well, I forgot pi over 4. So definitely pi over 4. They will actually be equal there. 3 pi over 4, they'll have different signs, but same absolute value. 5 pi over 4, they'll both be negative, they'll be the same. And then 7 pi over 4, sine will be negative, but they'll have the same absolute value. And so it's not too hard to see that at pi over 4, what's going to happen? Well, between 0 and pi over 4, cosine is going to be bigger than sine. So that means before pi over 4, so between 0 and pi over 4, function is going to be concave up. And then between pi over 4 and 3 pi over 4, sine will be bigger. Just look at the unit circle. The y-coordinate will be bigger, closer to pi over 2. So it'll change from positive to negative. So let's just see. It'll be positive and then negative and then positive and then negative and then positive. Okay, just by looking at the unit circle, we see that cosine squared is bigger, and then it'll be smaller, and then it'll be bigger, and then it'll be smaller, and then it'll be bigger. So all of these are inflection points. So we have 4 inflection points. Alrighty. So you see where knowledge of the unit circle really helps out. Otherwise, you're going to be plugging a ton of numbers into your calculator, which you can do. And if you don't believe me, I encourage you to do that. Just actually sit there and verify. But it's a little bit easier if you have a good understanding of the unit circle. So next, let's list the intervals in concavity. So H is concave up. Here, here, and here. So 0 to pi over 4, union 3 pi over 4 to 5 pi over 4. And then 7 pi over 4 to 2 pi. And then H will be concave down. Here and here. So between pi over 4 and 3 pi over 4. And then between 5 pi over 4 and 7 pi over 4. And then we are done. So that's how it goes. As you can see, hopefully you're starting to believe me that this is the most challenging part, because what's coming next? Well, to graph a function, we basically need to do all of this. We also need to go back and think about end behavior, so take some infinite limits, see where we have asymptotes, and then combine everything together and try to sketch the function. So we're going to do a couple together. Try to hang with me. Alright, so we're ready to start trying to graph functions, to sketch curves. Okay, here's our function f of x. As you see, it's not too difficult. You can imagine that if you had a very difficult function, this would be very difficult and just kind of a pain. I mean, it's still a pain, but let's at least go through our guidelines and just go step by step. I mean, really, you got to think that this sort of problem is like 10 problems in one, really. So let's just go through. And the guidelines are there to just sort of tell you step by step what to do and gather the necessary information to sort of accurately draw the function or sketch the curve. So the first thing we want to do is find the first and second derivatives and the critical points. That's pretty straightforward. And as you'll see, most of these steps are not difficult in and of themselves. It's just a matter of doing all of them. Okay, so that should be the derivative. And then the second derivative is 12x squared plus 24x. When is f prime equal to 0? Well, we can kill a factor of 4, and so we have x cubed plus 3x squared is 0. And if we factor out an x squared, we see that x squared can be 0, or x plus 3 can be 0. So our critical points of our function our x equals 0 and x equals -3. So for x equals 0, unfortunately we can't use the second derivative test. If we try to evaluate the second derivative at 0, we're going to get 0. So the second derivative test is inconclusive. But if we just look, if we plug in, say, -1, okay, so that's going to be -4 plus 12, that's going to be positive. And then if we plug in 1, we're going to have 4 plus 12, that's 16, that's also positive. So f prime does not change sign. At x equals 0. Okay, that means it's not a local extrema. It's not a maximum. It's not a minimum. But for -3, I think we can actually use the second derivative test. So f double prime of -3, so this is going to be 12 times 9, okay, minus 24 times 9. Sorry, 24 times 3. And now you can just plug that in and get it. But now because 12 and 24 differ by a factor of 2, and then 9 and 3 differ by a factor of 3, 12 times 9 is bigger than 24 times 3. Is the, so let's just do it. 12 times 9 is 108, and then 24 times 3 is 72. So it's 108 minus 72, whatever, it's positive, okay? I mean, if you're not convinced, just plug in -3, and you're going to see the second derivative at x equals -3 is positive, which means f of -3, which we should probably get that value because we want to plot these points. F of -3 is -27. This is a local min. All right. And now this is the only point where the function or the derivative changes signs. Okay, so we know it's going to be increasing to the left and increasing to the right, well, except at x equals 0, right? Because actually at x equals 0, it's not increasing or decreasing. So let's see. So f is going to be decreasing. So from -infinity to -3, because -3 we have a local min, so it's going to be decreasing and then increasing. And then f is increasing. So maybe there's a little, discrepancy about at 0. It would probably be fine if you just said f is increasing from -3 to infinity. But because we have this correlation between the derivative being positive and a function being increasing, we'll just say it's not wrong to say f is increasing on -3 to 0, and then at 0 the derivative is 0, and then increasing from 0 to infinity. That's kind of a very small, subtle technical point that, really is not worth diving into too much. Okay, so, well, you can already see I'm getting a little out of order of our guidelines, but, I mean, they're just guidelines. So we found first and second derivative, we found the critical points of f, and then we determined the local extrema. So now let's do the same thing for the second derivative. So what are the critical points of the second derivative? Or the critical points of the derivative, the x values that make the second derivative 0. So if we set f double prime equal to 0, we can factor out a 12x. So we have 12x times x plus 2 is 0. And we get x equals 0 or x equals -2. Okay, and now we just need to test around these critical points. So if I plug in a negative number, so a number, let's say less than -2, well, this is going to be greater than this if I plug in a number greater in absolute value than 2. So it seems like at x equals -2, so let me actually write these this way, just so they're in order. If we have x equals 0, that's a point where potentially the concavity changes. I did it again. -2, and x equals 0. If I plug in a value into the second derivative less than -2, the second derivative is going to be positive. Okay, I plug in -3, get a positive number. If I plug in -1, that's going to be negative. And if I plug in any positive number, of course, the second derivative is going to be positive. Let's plug in 1, say. So I see that both of these are inflection points. Are inflection points. And I actually want to go ahead and find the function values there too, because I'm going to plot the inflection points. So we have -2, comma, -16, and then 0, that's just going to be 0. So here are my inflection points. And we've also determined the intervals for which f is concave up and concave down. So f is concave up from -infinity to -2, and then from 0 to infinity. And then f is concave down between -2 and 0, because the second derivative is negative. So between -2 and 0. All right. So again, it's important to keep all of this information relatively organized. Okay, so where are we? We are through step 3 in the guidelines I gave you. We found the first and second derivative. We found the critical points of the function in the derivative, the potential extrema and potential inflection points. We determined what the local extrema were. We determined what the inflection points were. And then we listed the intervals for which f is increasing, decreasing, concave up, concave down, so that we can accurately now portray those different parts of the function. And then number 4, remember, is the catch-all. And now the good news here is that this is a polynomial, f of x, so there's not going to be a lot of crazy asymptotes or anything like that to describe, but we should just note the end behavior. Okay, so because this is an even degree polynomial, we know the limit is x goes to infinity is infinity, and the limit is x goes to minus infinity is infinity. Okay, so here's all of our pieces of the puzzle that we just need to kind of stick in. So, the other thing that I mentioned about plugging in are the x and y intercepts as well. So we know we have an x and a y intercept at the origin. We pass through the origin. That gives us the y-intercept. But is there another x-intercept? Well, does f have another 0? Well, it does, right? So if I set f equal to 0, that's saying that x cubed, so I'm just going to factor out an x cubed, times x plus 4 is 0. So x equals 0 we already knew about, but there's also a 0 at -4. So f of -4 is 0. Again, that just gives us another anchor point to plot and just make our sketch of our graph a little bit more accurate. Okay, so we are through kind of the initial stages. The last step is to plot all of the points, the critical points, inflection points, intercepts, and then connect the dots in a way that accurately portrays when the function is increasing and decreasing, or concave up or concave down. And specifically, which combinations, there's 4 possibilities that the function could be in between any of those 2 points, extrema or inflection points. So let's just do it. So I'm going to pull up the graph and then we'll talk about it. All right, there it is. Beautiful. And again, I told you I was going to cheat because I'm deathly embarrassed of my drawing skills. But I think that if you were really careful, you could sketch by hand this exact graph, okay? And really, everything on this graph is just accurately portrayed from the information we already found. So notice the points I plotted. So this was an intercept, -4, 0. This was a local minimum, -3, -27. That's what it was. Yep. This was -2, -16, so an inflection point. This was our local min. This was another inflection point, 0, 0. So it changed concavity. And now here's what I really want you to notice. So right here, between -4 and 3, between these 2 dots, the function is drawn decreasing in concave down. So decreasing, concave down. Between these 2 points, just using the intervals that I knew the function was increasing and still concave down. So increasing, concave down between those 2 dots. Then the function was still increasing, but concave. Oh my goodness. I just realized I'm being quite silly. Concave up. I don't know the difference between concave down and concave up. No, the function is concave down right here. So here, between here and here, it's decreasing and concave up. Here it's increasing and concave up. Here, it's increasing. But at this inflection point, it became concave down. And then at this point, it stays increasing, but changes back to being concave up. Okay, so you see I have accurately portrayed, once I got all of my bearings straight, where the function is decreasing concave up, where it's increasing concave up, where it's increasing concave down, and when it's increasing concave up. And that's basically it with curve sketching. And as you can see, so if you did this yourself, or you tried to do this yourself, you would not be able to do much better than this. And the computer cannot do much better than you, just based on your eyesight. I mean, this decreasing concave up piece, that's it. Increasing concave up piece, that's it. As long as you sort of connect your points together in a kind of a smooth way, your graph will be, to your own eye, almost as accurate as the actual computer graph of the function. So it's really nice, and it's really cool. It's really involved, but there's a lot of payoff. And if you can do this sort of analysis of functions this way, to the point where you can sketch them You are becoming a master of understanding functions and understanding how they change. And I told you at the beginning of this course that calculus really was about functions and how they change. So understanding these principles are going to allow you to succeed when it comes to doing applications. Okay, one more function to sketch, and then we will be masters of curve sketching. So first things first, easiest thing to do, don't even think. You're in calculus, you have a function, take derivatives. Now I'm going to skip some steps just so we eventually get to the good stuff. I'm just going to tell you what the derivative is simplified. So the derivative is negative x plus 2 over x cubed. And then the second derivative is going to be 4 times x plus 3 all over x to the fourth. Okay, so just some applications of the quotient rule and then getting at common denominators, etc. That's it. Alrighty. So let's get to work. First thing we need to do is find critical points. So when does f prime equal 0? I'm going to make a note first about x equals 0. So recall that the domain of this function, this is really important, is negative infinity to 0 and then union 0 to infinity. Because we can't divide by 0, but what that means is for the first and second derivative, we can actually just ignore the case where they're undefined because the original function is undefined. So that's something. So that means we only have one critical point for f prime equaling 0. And that's when the numerator here is 0. So in other words, when x is equal to negative 2. Okay, so let's second derivative test this. What's f double prime of negative 2? Well, 4 times negative 2 plus 1, negative 2 to the fourth is positive. Looks like we have a positive over a positive. So this is going to be positive. So that means that f of negative 2, so what's f of negative 2? Maybe that's the hardest part, adding fractions. Well, it looks to be 3/4. I don't think that's too bad. F of negative 2 is 3/4. And this is a local min. Local min. Okay, and that's our only local extrema, actually. Alrighty. Now we move on to the second derivative. Well, I guess we can first talk about the increase and decrease. So because we have one local min, now we do need to consider the case to the right of 0, because actually when x equals 0, you could change from being increasing to decreasing. But let's just think. So f is increasing. On, well, definitely between negative 2 and 0. Right? And notice I'm stopping at 0 because there's something going on with the function at 0. Okay, so actually there's an asymptote, but let's not even talk about that yet. Okay, but because there's an asymptote, there's a discontinuity in the function. So I really want to treat the part that's 0 to infinity separate from the part that's negative infinity to 0. So if I plug in, say, x equals 1 to the derivative, well, I'm going to get a negative number. So it's actually decreasing from 0 to infinity. So f is decreasing on, well, negative infinity to negative 2. I know that's true because I have a local min at negative 2. But then also 0 to infinity. And again, that's just coming from the fact that if I plug in a positive number into the derivative, I'm actually going to get a negative value. Okay, so that takes care of the first derivative information. So let's move on to the second derivative. When does f double prime equal 0? Again, I'm going to ignore the case where it's undefined. So the second derivative is 0 when x is negative 3. And it's very easy to see, right, that the second derivative changes from being negative to positive at x equals negative 3. If I plug in something to the left of negative 3, say negative 5, notice the denominator is always positive. I'm going to get a negative number, and if I plug in something positive, well, I'm going to get a positive number. So x equals negative 3 is an inflection point. So let's actually write down the function value so we can plot it. So negative 3, if I plug in negative 3, what do I get? Well, add some fractions, you'll get 7/9. So negative 3 7/9 is an inflection point. Excellent. Making some good progress. And now this tells us some good stuff. So f is going to be concave up. Well, after negative 3, so even if I go to the other side of the vertical asymptote, so between 0 and infinity, if I plug in a positive number to the second derivative, it's going to be positive. So it's really concave up from negative 3 to 0, and then also from 0 to infinity. And then it's concave down basically to the left of negative 3. So negative infinity to negative 3. All right, very good. So let's look back at our guidelines because, when you're doing this, if you're like me, you probably forget what you're even doing. So we want to make sure that we've done everything. So we found the derivatives, found the potential extrema, potential inflection points, actually nailed down what the extrema were. We had a local min, and what the inflection points are. We had one inflection point. We listed the intervals for which f was increasing, decreasing, concave up, concave down. So the final thing to do before we are ready to actually do the drawing is this kind of catch-all about asymptotes and intercepts. Now, notice, first and foremost, that there is no y-intercept because I can't plug in x equals 0. So just a couple notes. No y-intercept, but also there's no x-intercept. And why is that? Well, if I try to set this equal to 0, then what I would get, if I rewrite my function and get a common denominator, I have x squared plus x plus 1 over x squared. And so for the function to be 0, I really need the numerator to be 0. But the numerator is never 0. And how do I know that? Okay, you're like, how in the world do you know that? Well, this goes way back. We did all that pre-calculus review for a reason. X squared plus x plus 1 is called an irreducible polynomial over the real numbers. What does that mean? It means that it has a negative discriminant. So if you look at that factor b squared minus 4ac, so that's going to be 1 minus 4, so negative 3. To find the zeros, we're going to have to take the square root of a negative number. So there are no real zeros. There are complex zeros, but no real zeros. So what that means is that the function is never going to cross the x-axis. So there are no x-intercepts. Pretty cool. Look at all that algebra we're using. It's just, and again, it's a lot, but I hope you stop and realize just how cool it is. Just that everything you've ever learned in your life is sort of somehow coming into play here. I think it's cool. And then the final thing is the vertical and horizontal asymptotes. And this is pretty straightforward because the limit as x goes to 0 is going to be positive infinity. How do I know that? Well, it's from this again. If I rewrite my function like this, as x goes to 0, so the numerator is approaching 1, and the denominator is going to be a small positive number. So it's 1 over small positive. That gives large positive infinity. Then the limit as x goes to infinity. Okay, this is just an application of, we won't justify it, but remember, this is a rational function, so the degree of the numerator equals the degree of the denominator, so we have a horizontal asymptote at the ratio of the leading coefficients. So same thing for minus infinity. Okay, so what does that mean? Well, it means y equals 1 is a horizontal asymptote. And then x equals 0 is a vertical asymptote. All right, super cool. So now we have a tremendous amount of information. And so we have it all organized here. And then the task, which is not so difficult to do. I'm not saying that it's impossible. I just always prefer to use a computer because it's going to, cover up all my flaws in my ability to draw things. But let me show you the graph, and then we'll go through and talk about all the different pieces that it took to actually plot the function. Ta-da! Here it is in all its glory. And so the only thing I didn't include are the asymptotes. So here's this vertical asymptote, x equals 0. And then also we have this horizontal asymptote, y equals 1. Okay, so we see the functions are kind of leveling off to these asymptotes. Okay, so notice the points I plotted. I plotted the inflection point, which was -3/7/9. A little tricky to plot. And then we had the local min. Kind of hard to see it's a local min, just because of the nature of the function. -2 3/4. This was a local min. This was an inflection point. Now the interesting thing about this function is that kind of in this region right here, even though technically it's going to be concave up, let's see, it's going to be concave, concave up, it's going to be concave down over here. You see the concavity is very close to 0. So if the graph ever looks really flat, it means either the concavity is exactly 0 or it's very, very close to 0. So the more concave it is, the more kind of bend it has. It's going to be more concave up right here. So over here, this is concave up and decreasing all over here. between -2 and 0, it's going to be concave up and increasing. Now, right here between -3 and -2, it's going to still be concave up. I know it's really hard to tell, but it's actually decreasing very slowly. So it's still very much concave up and decreasing. But then actually to the -3, this is even harder to see. It's concave down and decreasing. So maybe you can detect just a very slight concave down bending, concave up bending there. Okay, so that is it. That's the function. That's what it looks like. We plotted all the relevant information. It's accurately drawn to show where the functions are concave up and concave down, increasing, decreasing. So that's the idea behind curve sketching. So one of the coolest, but definitely one of the most tedious and technical and intricate parts of this course. But again, if you followed all this and you mastered curve sketching, if you're able to do these on your own, then you are about to reach Calc Master level. So this is something that, I would spend some time on, make sure you practice, do some more examples on your own, and get the hang of it.